In this lecture, we're going to be talking about three-phase inverters with resistive loads. So I've gone ahead and drawn the circuit for a three-phase inverter here on the left. And as you can see, we have 6 transistors, and then we have the DC voltage input, and we have a set of three-phase voltages at the output. And so this is a typical configuration for a three-phase inverter, and you can see that there's 3 legs on the inverter. And so what we're going to do is we're going to call this transistor pairs a leg of the inverter. So in other words, transistors Q1 and Q2 form the A leg, then transistors Q3 and Q4 form the B leg, and transistors Q5 and Q6 form the C leg. And so you can see that I've connected the positive terminal of VA, VB, and VC to each one of these legs. And so remember that what we're trying to achieve here is we're trying to make a balanced set of three-phase voltages at the output, meaning that VA, VB, and VC are going to be equally spaced out 1/3 of every cycle from each other. And so the switching of these 6 transistors is going to be a little bit trickier than the single-phase inverter that we looked at, because now we're trying to simultaneously make 3-phase voltages at the output. And so let's see how we can achieve these 3-phase voltages. Let's say, for example, let's begin by saying that we're trying to make VA positive. So let's say that we're going to turn transistor Q1 on. So let's go ahead and write that down. We're going to say that state 1, Q1 is going to be on. But now we need to make somehow a difference in potential for VA from the other 2 legs. And by the way, here, one thing that we cannot do is we cannot switch 2 transistors from the same leg, or rather both transistors from the same leg on at the same time. So for example, if we were to switch Q1 and Q2 on at the same time, then we would be shorting out the DC voltage input. And so we cannot do that. So we know that for a fact, if we're trying to make a positive voltage at VA and we have turned Q1 on, then we know that we cannot turn Q2 on because that will short out the input. So now we need to take a look at the other 2 legs and see how we can make a voltage difference for VA. And so let's say, for example, that we switch Q4 on and we're going to switch Q5 on as well. And by the way, at any point in time, we're going to switch 1 transistor on from each leg. And that's going to help us make the 3-phase voltage output. So let's see what happens when we switch Q1, Q4, and Q5 on at the same time. So you can see that basically we're going to connect the positive terminal of VN to the positive terminal of VA through Q1. So I'm going to go ahead and draw here in yellow basically the circuit that we're going to make by switching these 3 transistors on. So we know that Q1's on, and then we're saying that we're going to switch Q4 on. So then we're going to connect the negative terminal of VN to the positive terminal of VB through Q4. And then we also said that we're going to turn Q5 on. So the positive terminal of VN is also going to be connected to the positive terminal of VC through Q5. And so the circuit will look like this. And so I know that this looks a little bit convoluted. So let's go ahead and draw the equivalent circuit for this inverter when we switch these 3 transistors on. So we would have VN, our input voltage source. And then we said that we've connected that to both the positive terminal of VA and VC. So this is going to be VA positive negative, and then VC positive negative. But then we've connected the negative terminal of VN to the positive terminal of VB. So then we can say here that we would have VB over here, but this would be plus and negative over here. And again, this is VB. And so I'm going to go ahead and define one more point. This middle point right here is what's called the neutral, which is basically this point right here. So now let's see what happens to the 3 output voltages. So first what we need to do is we need to determine what potential there is at the neutral, because we know it's not going to be 0, right? Because we've connected Vn through A and C and B in some configurations such that we know that the neutral cannot be at 0 volts. And so in other words, let's call the voltage at the neutral Vn. And if we do a simple voltage divider to calculate the voltage at the neutral, we would get that Vn would be equal to Vn times the resistance of the B load, so let's call that RB, over RA and RC in parallel, plus RB. So this is the equation for a voltage divider. Basically, we're trying to calculate the voltage at the neutral based on the configuration of RA, RB, and RC. And one more assumption that I'm making here is that the output load is balanced, meaning that RB is equal to RA and RC. So the load on all 3 phases is equal to each other. And so from basic circuit analysis, I'm going to go ahead and replace the RA, RB, RC with just R, because again, they're equal to each other. But from just basic circuit analysis, we know that if we have 2 resistors in parallel of the same resistance, then the equivalent resistance is going to be half of the resistance. So in other words, if we say that RA is equal to RC in ohms, and RA and RC are in parallel, then we know that the equivalent of the combination of those 2 in parallel is going to be equal to half of that resistance. So we can say then that this right here would be 0.5 times R plus R. So then Vn would be equal to Vn times R over 1.5 times R. So this is going to be equal to, and of course the R's cancel out, this is going to be equal to Vn over 1.5, which is also equal to 2/3 of Vn. So now let's see what the output voltages will look like. We know that VA is connected to the positive terminal of Vn. So let me go ahead and write that here on the top. So VA is going to be equal to whatever's connected at the positive terminal to minus whatever's connected at the negative terminal. So we know that at the positive terminal of VA, we have Vn. So it's going to be equal to Vn minus the neutral voltage, which we've established that is 2/3 of Vn. So minus 2/3 of Vn. And so this is going to be, of course, equal to 1/3 of Vn. And so I've gone ahead and drawn here on the axis on the right 2 voltage magnitudes. And that's because I knew that this was going to be 1/3 of Vn, and this is going to be 2/3 of Vn. And likewise for all the other voltages. So minus 1/3 Vn minus 2/3 Vn, and likewise for the B and C phase. So I'm going to go ahead and write that down real quick. Okay, so we know that VA is going to be equal to 1/3 of Vn. So let's go ahead and draw that here on the top. So let's see what VB would look like. So VB is going to be equal to whatever is connected to the positive terminal of VB, which is the negative terminal of Vn. So, but we're going to say that the negative terminal of Vn is going to be at 0 volts. Basically, we're going to say that the positive terminal of Vn is whatever Vn is, and then the negative terminal of Vn is going to be 0. So we're going to take the negative terminal of Vn as the reference, essentially. So then VB would be 0 because it's connected, because the positive terminal of VB is connected to the negative terminal of Vn. So 0 minus whatever is connected to the negative terminal of VB, which is the neutral voltage, which was said that is at 2/3 of Vn. So then VB would be equal to minus 2/3 of Vn. So VB would be over here. Now we can do the same thing for VC. So VC is going to be equal to whatever's connected to the positive terminal, which is Vn, because again, Q5 is on. So we've connected the positive terminal of Vn through Q5 to the positive terminal of VC. So Vn minus the neutral, which again is 2/3 of Vn. So VC, just like VA, is going to be equal to 1/3 of Vn. So it's going to be over here. So this is starting to take shape. And you may have noticed that I've divided one period in 6 steps. So if we say that one period is 2 pi, then these waveforms are going to have 6 different voltages throughout them. So basically we're going to have 6 different combinations of switching transistors Q1 through Q6 to make the 3-phase voltage output. And so what we're going to do for each one of those steps is we have to do this calculation again. Basically, we got to draw the equivalent circuit based on the transistors that we're switching on and off to calculate what the neutral voltage is going to be at. And then we can calculate what the phase voltages are going to be by doing this calculation. Basically, whatever's connected to the positive terminal of that voltage minus whatever the neutral voltage is during that step. So let's do 2 more of these steps, and then we're going to see a pattern, and we can kind of see what the rest of the steps are going to be based on that. So in the next video, we're going to take a look at what the 3-phase output voltages are going to look like for the next step.